Hi, I am Mário Vilas Boas, and this is a lecture entitled Facts About Global Warming that Most Environmentalists Do Not Know About. Because it is too long, I divided it in two parts. This is part 1, an introduction to physics. Why have I made that? I made that because I've noticed that most people that has strong opinions about global warming caused by global warming gases, about greenhouse effect, they simply don't know some issues that are crucial, really important to argue about something, to defend an opinion about it. So I have listed some of these facts, and in this part 1 I will talk about some of them. It's just this introduction to physics. Okay, let's begin. The first issue I would like to talk about is units of concentration. This seems silly, but I have seen a lot of people that speak about that without knowing what is he speaking about. It's really amazing how people commit mistakes about such a simple thing. Environmentalists say that carbon dioxide concentration in atmosphere is around 400 ppm. Well, this seems simple. This seems that there is nothing strange or nothing to talk about. But yes, there is. What does ppm stand for? Some people say it by extents. ppm stands for parts per million. But the tricky thing is the word part. What does part mean? This concept is borrowed from chemistry. And in chemistry, when you say part and don't specify what we are talking about, we mean weight. So what does 400 ppm stand for? Or 400. That means that 1 ton of air has 400 grams of carbon dioxide. Is that what it means? Well, we must say that this statement is false. Although it's not forbidden to measure gas concentrations in ppm or in weight fraction, this is not usual. Generally, we measure gas concentrations in volume fraction. Why? Because most instruments we have for analyzing gas composition, they give the result in mole fraction. And when you deal with gases, mole fraction equals to volume fraction. Therefore, the correct concentration of carbon dioxide in atmosphere is 400 ppmv. That means part per million in volumetric basis. That means that 1 cubic meter of air contains about 400 millimeters of carbon dioxide. If you convert that to ppm, which means weight fraction, it will give about 600 ppm of carbon dioxide in atmosphere. Someone that asks about global warming due to greenhouse effect and does not know the difference between weight fraction and volume fraction and does not know by heart what does this number 400 or whatever state for, if it is weight fraction or volume fraction, he doesn't know what is he talking about. So that's the first thing. Now, the second issue is carbon versus carbon dioxide in atmosphere. The chemical reaction of burning of carbon is this one that appears there. 1 mole of carbon reacts with 1 mole of molecular oxygen and produces 1 mole of carbon dioxide. What does it mean? 1 mole of carbon weighs 12 grams. 1 mole of oxygen, molecular oxygen, weighs 32 grams. And 1 mole of carbon dioxide weighs 44 grams. That means that burning 1 ton of carbon will add in the atmosphere 1 ton of carbon in form of carbon dioxide. Is this the same thing of say that 1 ton of carbon will add on in the atmosphere 1 ton of carbon dioxide? No, this is false. And whoever says that does not know what is it talking about. Burning 1 ton of carbon will add up in the atmosphere about 3.67 tons of carbon dioxide. And beware, anyone that does not know the difference between carbon in the atmosphere and carbon dioxide does not know what he's talking about, including the fact that carbon in the atmosphere does not mean only carbon dioxide, because there are some other gases in the atmosphere that also contain carbon, such as carbon monoxide and methane. However, the amount of those gases are very small, so this last error is a forgivable error. But say that 1 ton of carbon in the atmosphere is the same thing of 1 ton of carbon dioxide is an unforgivable error. Well, the third issue is Planck's law about the black body. Well, I'm sorry to say that this is a very long and complex chapter of the physics. However, it is absolutely not possible to understand the greenhouse effect without having at least a brief understanding about this phenomenon. So I will have to explain it here, but in order not to make this lecture too long and too boring, I will be very superficial in this describing of this phenomenon. The first thing is to understand what happens when a beam of light reaches a surface of a body. 3 things can happen when this beam of light hits a body. The first thing is that the beam of light may cross the body, like this you see in the figure. However, this will happen only if the body is transparent. If the body is opaque, this will not happen. Nothing will cross it. So let's talk from this point on about opaque bodies. So no fraction of the incoming light will cross the body. So if it will not cross the body, there are 2 other things that can happen. The beam of light may be reflected, like you see in the figure, or it may be absorbed. If it is absorbed, then it will change in another kind of energy. The energy contained in the beam of light will be changed. It may be changed, for instance, in electricity in a photovoltaic cell, or it may change in chemical energy in the leaf of a plant. But most often, it will just change into heat, and this heat will increase the temperature of the body. Well, now let's see what Planck's define of a black body. A black body, according to Planck, is a body that will absorb all the incoming light. no fraction of the incoming light will cross the body or be reflected by it. Everything, every bit of energy of the incoming light will be absorbed. This is a black body according with Planck's law. And why is this important? Let's see first what a black body is. Recently, a company has developed a paint which absorbs 99.96% of the incoming light. This is the closest of black that we have ever been produced. Well, this movie you can see right here is what happens when you paint a simple object with this paint. Look at this movie. You can't see absolutely any light coming from the body. Therefore, you can't see any details of it. This is the shape of a face, a human face. However, you see one of the bodies which is not painted. You can see eyes, nose, mouth, ear, mustache. Look at the black one. You can't see anything of this. Well, within 0.04% error, this is a black body. But this is a black body when it is cold. What happens when the black body is not cold, when it is hot? A black body, when it's hot, it shines. But this is the tricky thing. How does it shine? Which color? Which wavelength it blows from it when it shines? Planck's law states a specific curve about wavelength. This curve will vary with temperature. As you can see here, the shape varies with temperature. When you increase the temperature, however, it changes the shape. All the wavelengths is emitted in a higher level than in the colder temperature. We need to know this in order to know what happens when a body absorbs light. Well, what if the body is not black? If the body is not black, we can call it gray or colored. A gray body is a body that absorbs less than 100%. However, the amount of absorption is the same at all wavelengths. This is a gray object. A colored object will absorb different in each wavelength, always below 100%, but different in different wavelengths. What happens when the not black body is hot? It shines, but it will shine in a fraction of the amount of the energy that a black body produces. Which fraction? The same fraction as it absorbs when it's cold. So, for a body which is not black, it will throw less energy than a black body. As you can see here, almost all the energy of a black body is in the infrared region, unless its temperature is very high. Earth is not a black body. However, we use the black body curve as a reference because we know that the amount of energy cannot, in any case, be higher than the one of the black body. So, although you do know that Earth is not black, we use always the black body curve as a reference. So, now that we have gone through all that, we are ready to know what is the greenhouse effect. So, the first thing is, why this name? What a greenhouse has to do with the greenhouse effect. Look at this picture. The greenhouse is a construction whose ceiling and generally also the walls are transparent. Generally, they are covered with glass. So, this is not obvious in this figure, but this is transparent only to visible light. It's not transparent to infrared. The photo does not show that. However, this is the case. You can see it transparent to visible light, but it's not transparent to infrared. So, what happens? When a black body is exposed to light, it absorbs the light. We have already seen that. Generally, this absorption generates heat. The energy from the light is converted to heat and the temperature increases. As the temperature increases, the body begins to shine. But it shines, unless the temperature is very high, it shines only in the infrared region. Now, if we put a transparent surface between the light and the body, what happens? If it is perfectly transparent, nothing happens. Continues to do exactly the same. However, if this surface is transparent, this plate is transparent to visible light, but not to infrared, what will happen? It will happen what you see in this figure. The energy from the light, high energy, will come in, it will heat the body. However, the temperature, the infrared that is emitting from the body will not go out. Therefore, the body will be heated much more efficiently. That's why some scientists say temperature inside the greenhouses are generally higher than outside due to this effect. Well, some scientists do not agree. Some scientists just say that the temperature inside is higher than outside because it's protected against the wind. Well, I'm not arguing about that. This is not the objective of this lecture. I'm just presenting. This is the concept of the greenhouse effect. So, now we are finally ready to discuss the greenhouse effect of the atmosphere. What all of those stuff has to do with global warming and greenhouse effect gases. Why? What does it have to do? Look, this picture represents more or less the Earth being illuminated by the sun. Between the Earth and the sun is the atmosphere. We used to think as the atmosphere as a transparent medium, but it's not the case. Like the glass, atmosphere is transparent to a certain range of wavelengths, but not to all the ranges. It is transparent to the light we can see, but within the infrared there are some regions in which the atmosphere is not transparent. But since we can't see, this is not obvious for us. Well, Lillesand and Kiefer in 1994 have measured the transparency of the atmosphere for various wavelengths ranging from visible from infrared. And they got this graph you can see here. You can see that there are some ranges in which the transmittance is very low, even it's zero. Transmittance zero means that region, atmosphere, is completely opaque to that wavelength. And it's interesting to see why it is opaque to the wavelength in certain ranges. Look at the picture. You see some blue rectangles and some orange rectangles, some blue ones, some red ones. The blue ones are absorption due to water. People don't say it, but water is also a greenhouse effect gas. The orange ones are due to carbon dioxide, and so are the red ones. So what is the difference? As you can see in the picture, the orange are in the orange ranges, the absorption is 100%. And in the red ranges, it's not 100%, it's less than that. Why is it important to make this difference? The importance of that is the following. What will happen if you increase the concentration of carbon dioxide in the atmosphere? This region in which the absorption is 100% cannot increase any longer. The only regions that can increase are the red ones. Now, we will superimpose this graph to the graph of emission of a black body at a temperature of 20 degrees. 20 degrees is considered the mean temperature of Earth's face. If you think this temperature is strange, it should be different from that, you must remember that this takes in account all Earth's surface, and 70% of Earth's surface is ocean. This takes this into account. So 20 degrees Celsius is considered a good representation of the mean temperature of the Earth. So a black body at this temperature will shine within this curve which is shown in the figure. Okay, so what? In order to see it more clearly, let's take the figure of the atmosphere, the transmittance of the atmosphere. Now you can see that what is blocking, let's say, the shining of the Earth is carbon dioxide, more or less in the range of 14 to 15 microns. That range, it is blocking a considerable amount of energy. A small range, close to 13 microns, also blocks something. And this one is not 100%, it's not blocking 100%. So if we increase the carbon dioxide in the atmosphere, the only increase we will have in the greenhouse effect is in this small range you can see in red in the graph. These are the facts. This is what happens. This is the physical phenomenon that govern the phenomenon linked to global warming due to greenhouse gases. So what we may conclude with those data? Well, since this movie has already been so long, we'll let this to part 2. Okay? In part 2, we'll try to find out whether the conclusions of the environmentalists are true or false. But we must always remember that these are the physical phenomena that govern these effects. So, see you in part 2. Goodbye.